同学再请你 check 一下。档机啊。在这里。OK。Okay. And yeah, so hopefully everyone now knows the classical complexity theory and the important concept of classical complexity. And now let's go back to quantum world. So now we have a basic idea of computer science. We can finally talk about quantum computation. We now know quantum, and we know computation. We can talk about quantum computation. So we start quantum computation with a circuit model. Okay. And yeah, so quantum circuit, just like a classical circuit, it has a wire and a gate. And then there is a extra thing that is measurement, because our quantum circuit will create a quantum state, and in the end, when we want to calculate some classical thing, we need to do measurement. Okay. And yeah, just like a classical circuit, we have those wires, and each wire is usually representing 1 qubit. So 1 qubit can be either 0 or 1 or superposition, etc. And each gate is now a unitary operator. We have a very strong restriction on gate, because as we say in our quantum postulate, any quantum operation you can do is a unitary operator. So every gate here is also a unitary operator. And so that means two things will happen here. So first, there is no fan out. You cannot have one wire become two wire, and this also just become, I guess this is more like under the wire. Okay, so you cannot have one wire become two wire because there is no cloning. And and also each gate will be reversible, because it's a unitary operator, and you can just find its inverse as this Dagger operator. You know, U dagger U is always equal to identity, so every gate you apply, you can apply its Dagger operator, and then you will invert your gate. Okay. And also there is measurement, and measurement will be, most of the time we assume the measurement is just in computational basis, because as we described in, I guess, first over the measurement, as we described in the quantum mechanics chapter, we say that computational basis measurement is actually computationally equivalent to all the generalized measurement. Remember, there is a theorem that we don't prove fully, saying that you want to do generalized measurement, you can just have an HR system and do computational basis measurement on the HR system. And in terms of quantum circuit, then that's very doable. You want to do a generalized measurement, you can get some HR wires as your HR system, and you do some more computation unitary, and you just measure on the HR system. Okay. So without lose of generality, we just assume the measurement at the end is classical. Okay. And yeah, but sometimes it's I guess this is usually, but sometimes people will say like measure in X basis instead of computational basis, and yeah. So maybe they will draw like a x and with measurement, and you know it's measuring the plus minus basis, etc. But most of the time it's still computational basis. And when you see measurement, it's usually this symbol. So we have this meter, means measurement, and then we'll draw the double line wire here. And the double line wire here means that it's a classical wire. So it's a classical wire, and it will carry 1 bit of classical information. So it's just either 0 or 1. Okay. So yeah, so we have wires and gates, and so we have some single qubit gate and some 2 qubit gates here, etc. Yeah. And so this is a quantum circuit, and it can have different input, different output. And but a lot of time the input will just be initialized as a 0 gate. Okay. But let's worry about inputs later. So let's first talk about gates. Okay. So gates can be really any unitary operator, but some unitary operator will like them more. Okay. And so the first four are very familiar for unitary operator. They are HEDMA, poly-X, poly-Y, poly-Z. Okay. So they are very useful because they have nice algebraic properties, and they are those unitary operator, and we should rememorize the entry. So let's go through it once again. So HEDMA gate is this 1 over square root 2, 1, 1, 1 minus 1. And the poly gate is this 0, 1, 1, 0. And the poly Y is this 0 minus I, 0. And poly Z is 1, 0, 0 minus 1. Okay. And so it's their matrix form. And in terms of drawing their circuit, and they are usually drawing in this way. So HEDMA gate is just a square with H inside, and we have X, Y, Z here. Square with X, square with Y, and a square with Z. Okay. So those four are the most common gate. 1 qubit gate we'll see, and then there are 2 other gates. Okay. It's a bit their name is a bit funny. Anyway, so there is a phase gate. Okay, so phase gate is basically the square root of the Z gate. So this 1, 0, 0 I gate, and phase. So in a textbook is written as S here, but sometimes people also call it P gate. So it's a square with P inside, and it's just P for phase. Okay, so this is S gate, and then there is also T gate. Okay, so T gate is just like you go from Z to S, you take a square root, then you take a square root of this thing, even more, then you get this T gate. So in this diagonal term here, you have square root of I is e to the I pi over 4. Okay, and I guess in terms of complex numbers, so just a few reminder on complex number. So if you have a complex plane, then you have a 1 here, and then you have a minus 1 here. This is e to the I pi, and then you have I here, and so the angle here is pi over 2, and then you have e to the I pi over 4 here. Okay. Let's try to draw better. Okay. The angle. Okay, so this is pi over 4, and so this point is this e to the I pi over 4. Okay. Okay, so it's 1 and e to the I pi over 4, and this is called T gate. Is something very nice. Yeah, but it's a bit hard to describe why people guess it's kind of a simplest thing that's far away from police enough. Okay, so this is a T gate. A lot of things we'll talk about T gate. And also it has a funny name. So you see you have e to I pi over 4 here, but it's actually called a pi over 8 gate instead of a pi over 4 gate. and this reason will be clear later. Okay, so this pi over 8 actually makes sense. Okay, because yeah, hopefully we'll get there today. Okay, and anyway, those are single qubit gate. They are 2x2 matrix that you can apply on a 1 qubit state. Any questions so far? Good. If not, then let's go to 2 qubit gate. And 2 qubit gate, basically the one used most is a CNOT gate, which is a really classical gate. You can also apply CNOT gate on a classical circuit, because this thing just map any computational basis to any computational basis. Okay. And let's see. So there is a matrix notation, but I guess it's easier to see what CNOT gate do here. Okay, so let's assume we have some computational basis AB as input to our CNOT gate, and so CNOT gate is written like this. There are two ways to write this. So either this with a solid dot here and how do I say, circle plus here, okay? Or it can be viewed as a control X here. Okay? And anyway, what this gate do is you have AB as input, and the output is so the first qubit will be called control qubit. So whatever computational basis input you have in, and they will have the same thing as output. Okay, and so control on this thing, what it do is it will flip on the second thing. Okay, so B will become B, and this O plus here means XOR. Okay. So A plus B means A XOR B, and this means A plus B mod 2. Okay. So these are some notation. I guess we didn't define before, we just define here. Okay. And what does this mean? It means that if A is 0, then B will stay the same. And if A is 1, then B will become B plus 1, which is the negation of B, because everything is mod 2 here. So 0 plus 1 become 1, and 1 plus 1 become 0. Okay, because this XOR means mod 2. Okay, and yeah, so from this interpretation, we see that Y is drawn here because it means control the X. So we think the first wire as the control qubit. The control qubit doesn't change, but it will depend on whether you want to do this ACE gate on the second qubit. So if control qubit is 0, then the second qubit doesn't change. And control qubit is 1, you apply the ACE gate on the second qubit. Okay. So it's a control X. And so it's control X, and it's also drawn, most of the time you will draw in this way. So control you usually draw with a solid dot, and then this X we just draw it like this. And yeah, so in terms of its matrix, because it's a control X, then it's a block diagonal with when the second qubit is 0, you apply identity on the first qubit, and when second qubit is 1, you apply X on the first qubit. On the second, sorry, when control qubit is 1, you apply X gate on the second qubit. And yeah, so you write all the four by four matrix. Then it's like this. So identity is 1 1 here, and X is 1 1 here. Okay, so this is a CNOT gate. And yeah, I guess one more thing I want to say is this is really a quantum gate. Okay, so this A and B here, we are just saying how it do on computational basis. But remember, this is a quantum gate, so we can really put any quantum state as input. So we can even put the plus minus as input, and we can even put the entangled state as input. We can put the EPR pair as input, and then you put a CNOT gate on it, and you get some output. And then how that actually do is, well, one thing you can do this 4x4, you can do this 4x4 calculation, or you can do by linearity. Okay, so I guess it's okay to do it here. Okay, so we can think about what if we have EPR pair as input. So let's say we have 0 0 plus 1 1, and let's be lazy and ignore the ignore the normalization. Sorry, I'm drawing this. So writing this in wrong order. So you have a C naught 0, 0 plus 1, 1. Okay. So what we do is we do this by linearity, and so this will equal to C naught 0, 0 plus C naught 1, 1, because C naught is actually a matrix, and let's go here out of empty space. And C naught 0, 0, now this 0, 0 is a computational basis state, and 1, 1 is also a computational basis state. So we can go by this rule. So C naught 0, 0, because the first qubit is 0, so nothing happened, is still 0, 0. And then C naught 1, 1, because the first qubit is still state 1, and the second qubit becomes 0, so becomes 0. Okay. And yeah, so this is the output, and this is equal to, you want to be a little bit more fancy, so it will be 0 plus 1 on the first qubit, and tensor 0 on the second qubit. And so here you see that you have an entangled state as input, then after you apply C naught, it actually become another entangled state. Okay. And I guess if we stop being lazy, and then we can write a normalization back. So it should be 1 over square root 2 here, 1 over square root 2, 1 over square root 2, and this whole thing 1 over square root 2, and 1 over square root 2 here. Okay, so this is how you apply a C naught. And also here we see something that's a bit funny about the circuit notation. That is the circuit using the input state on the left hand side, and you apply gate to the right hand side. So time kind of go to the right side, right? So if I get this way. But when you write the equation, then we have the input on our right hand side and get one by one on the left hand side. So this is a bit confusing, so don't mix it up. Okay. So the left and right ordering of when you write down an equation and when you write down a circuit is reversed, and sometimes it's a bit confusing. Okay. And yeah, so the C naught gate is the most common 2-qubit gate we'll see. And then there is a close cousin, it's a CZ gate. So now it's a totally quantum gate, and you probably guess from its name. So this is a control Z gate. So it's just like control X, but instead of X here, you do Z gate here. So it's when first qubit is 0, you do nothing, and the first qubit is 1, you do Z gate. So you write down the matrix. It actually has a nicer form than C naught. It is a 1, 1, 1 minus 1 matrix. It's fully diagonal. And you can see this is a quantum gate now because you actually get a phase here. You have a minus 1. And there is no classical way to describe a minus 1 phase. Okay. So CZ. And CZ is very nice because it actually is symmetric between its first qubit and second qubit. Okay. Because it's easy to see that if you control on second qubit and do the gate on the first qubit, you also get this thing. You also get this matrix. Okay. And excuse me. Yeah, so it's symmetric on first qubit and second qubit, and people will actually draw CZ with this kind of funny notation, and it's nice to remember it. So it's actually just a wire with two control. Okay, so you just draw a straight line and two solid dots on the both qubits. So because you don't know which qubit is actually control, so we draw both of them as a control. Okay, so that's a CZ gate. It is a funny syntax. And I guess to prove that it's actually symmetric, we can just write down how it acts on computational basis. So we think about CZ on some computational basis state AB is just equal to -1 to the A times B and AB. Okay, so only when both A and B equal to 1, you have a -1 factor in front. Okay. So that's CZ. And I guess we can have a more generalized control unitary. Okay. So We can have a control X, control Z, and we can really control any single qubit unitary. So we'll draw like this, just like before. So we have a control register with this solid dot, and we have a line down here. Then we go to this block of unitary U. So we have whatever unitary here. And in terms of its matrix, its biodiagonal term will be this identity and the U here. And if you do this on some input state, A being computational basis, and whatever state side here will be A and U to the A side. And we have U to the A here because A equals to 0, then we have identity here. And so U to the 0th power. I guess technically we haven't talked about how matrix are exponentiated, but we will probably talk about that today. But 0th power of any matrix equal to identity. Okay, so that's I guess a bit of a spoiler. U to the 0 equal to identity matrix. Just like in scalar computation, you have any power to a 0th power is equal to 1. Okay, and so yeah, any matrix to a 0th power is identity, and a matrix to the 1th power is the matrix. Okay. That's control unitary, and there is a swap gate. That's not too critical, but very nice to have. So it's when you want to swap two qubit. Okay. So if you can, if you want to swap this qubit and this qubit, sometimes you can think about. So physically, you can just reroute your wire. You can pull this wire down and pull this wire up. But if you want to write that as a gate, then you can have a swap gate. And it's right here this way. We have a cross here, and connect with a line. And yeah, so if you do this on computational basis, AB state it should become a BA state. Okay. And swap gate has a nice decomposition from just doing CNOT gate. So you can actually do 3 CNOT gate and get a swap gate. Okay. And let's see this actually work out. So on computational basis, you have AB inside, and so input is AB, and you do first CNOT, and you should do this thing. So it should become A on first register, and A plus B on second register. And then you do this, so then you do this reverse connected CNOT. Okay, and excuse me, and yeah, so we do a simple calculation. Now this is the second qubit is the control register, so it stays as A plus B, and the first register got the second register added on. So we have A, O plus A, O plus B, and then this XOR or this addition mod 2 are really commutative, so you can just have A plus B, and we have A plus A equal to 0 mod 2. Okay, because it is twice A and 2 equal to 0 when we mod 2. Okay, and so first register just become B, so we have a B and A plus B. Okay, after the second CNOT. And finally, after the third CNOT, we add this B to A plus B again. And once again, B plus B equal to 0, so we have a BA as the end result. Okay. And yeah, so here we define swap gate as something that will swap computational basis element. So we have AB being computational basis, and we get a BA. And but really we want to swap any quantum state. So maybe you have a plus state here and a minus state here. We want to that you do a swap gate, you become the minus state and the plus state. And yeah, so you can prove that this is actually true, and I think it's in your homework. So maybe you can add this also in our homework. Hopefully you haven't posted it. Just post it. Maybe next time. Okay, maybe next week. And anyway, you can try this in your homework and see that you do any pure state psi and phi, and you apply swap gate, you become phi and psi. Okay. So this is swap gate. And okay, so we have 1 qubit, 2 qubit, and we can have a 3 qubit gate. And I guess the most famous 3 qubit gate of quantum computation is this Toffoli gate. Okay, this is once again a classical gate. And oh, here I guess I should have O plus here. Okay, O plus. Okay, and once again it's a classical gate and it's a control NOT gate. So there are 2 qubits that are control, and third qubit you apply a NOT gate here. If only if both the first qubit are 1. So only when both of those control are like turn on, so you have a 1 and 1 here, then you will flip the second qubit. So sorry, flip the third qubit. So we have CO plus A times B here. Okay. So CO plus this number that's equal to 1 only if both A and B equal to 1. And so this is yeah. So in terms of a bit of a bracket notation, we have Toffoli ABC equal to AB and C plus AB. Okay. And as we said, AB equal to end of A and B. AB equal to 1 only if both A and B equal to 1. Okay. And oh, I guess here we want to say other thing. Okay, so why do people like Toffoli gate? Because because of classical computation. And Toffoli gate is a universal gate for classical reversible computation. Okay. And so we know that if we can apply it, we can implement Toffoli gate, then we can do every classical computation. And yeah, a lot of the time we do quantum computer, we actually want to do some classical computation in superposition, and that's why people like to apply do Toffoli gate. And there are also other reasons you want Toffoli gate, but this is a big reason. And yeah, so basically every classical computation you can do on quantum circuit, you can do with Toffoli gate. And here we also have a reversible here, and we need to have a reversible here because we need to have a reversible here because quantum circuit is always reversible. And also here we want to show a little bit about why it's reversible, because you can use Toffoli gate to calculate the AND gate. So if you just set C equal to 0 here, then the output will be AB and then there will be AND. And we know AND gate and NOT gate is enough to give you universal classical computation. Okay, so that's a Toffoli gate. And let's see some calculation example. Okay, so I guess this is a bit of a easier example than example already give. Okay, so first we have copy classical data. So you have a superposition state here, A0 plus B1 on the first qubit and 0 on the second qubit, and then we do a C naught. And then remember C naught AB equal to A and A plus B. And then we want to know what is this thing. Okay. Okay. And so first let's see what okay. And so what happened is because here we yeah, so we have input is A0 plus B1 and tensor this is 0, and and let's write down this input out into summation of two computational basis terms. So it's A over 0, 0 plus B over 1, 0. And when you do C naught on this thing, then you have C naught on A00 becomes still A00, and C naught on B10 is so you have 1 adding on 0 become 1, so B over 1, 1. And yeah, so you see that the C naught gate can create entanglement because you start with a non-entangled state, this is A0 plus B1 tensor 0, and then get this A00 plus B1, 1. And if none of A, B equal to 0, then this is an entangled state. And yeah, so this is why we always want the 2-qubit gate. So I guess this is why people want a C naught gate, because it's a gate that will create entanglement. And I guess something you can say here with it's easy to see that with only 1-qubit gate, you cannot create entanglement. Okay, it's quite obvious. Because you have a tensor product of states and you only do one cubic gate, you still have a tensor product with other states. Okay? Cannot create entanglement. Okay. So if you want entanglement in your quantum circuit, you must have two cubic gate, and the gate that people use most often is this CNOT gate. Okay. And let's see more calculation, and this is quite a random result. So we have AB. We have random AB computational basis as input, and we go through this circuit with Z gate and a Z gate and a CNOT gate, and want to show that this Z gate with CNOT gate is actually same as CNOT gate and Z gate, and we can do computation. So if we go through this circuit, then our AB, when we go through this Z gate, we will get a -1 to the A, because well, that's what Z gate do. Z give you a -1 to whatever your qubit is. Okay, when A equals 1, you get a -1 phase. A equals 0, you get no phase. Okay. So you go to Z gate, you get -1 to A, B, and then you go through CNOT, and then it's AB become A and A plus B. Okay. And but if you go through this circuit instead, so first you go AB, and then go A and A plus B, and then you do Z gate. Once again, you have a -1 to the first register, so -1 to the A and A plus B. Okay. So here we use this bit of computational basis algebra to prove that this circuit is equal to this circuit. Okay. And now let's see more entangling example of CNOT gate. Okay. So I guess this is a small component that we already used in previous example. Okay. So this is a circuit where of how you create the EPR pair. So you start with both K0 on your 2 qubit, and the first qubit you get you put a hidden mark here. So this becomes a plus state here, which plus state is equal to 1/2 1 over square root 2 0 plus 1. So you have a plus state here. And the second qubit is still 0, and then you apply your CNOT gate here. And so 0 0 is still 0 0, and 1 0 will become 1 1. So you kind of classic, you kind of copy the first qubit to second qubit, because 0 still 0 and 1 0 0. First qubit is 1 0, then it's 0 0. First qubit is 1, it's 1 1. Okay, but it's an entangled state because this 1 1 and 0 0 is in superposition. Okay. And then I guess this other thing you can check yourself. So as an exercise, you can check that this circuit is something that map a computational basis state to Bell basis states. And this is something that we'll use a lot. Okay. Actually, we have already used this when we construct our supertext coding and teleportation, and which we will see very soon. Okay. So what we mean is that you have other than 0 0, say you have 1 1, then you will get beta 1 1, etc. Okay. So you have if you have A and B as input, then output will be beta AB. Okay. I guess let's write this in a better form. So means that we'll map AB to beta AB. Okay, so this is a very nice circuit to remember. It will change from computational basis to Bell basis. Okay, and now we can see supertext coding a little better as a quantum circuit. Okay, so that remember a little bit about what is super dense coding. So super dense coding kind of start here. It says that Alice wants to send 2 qubit to Bob by by sending 1 quantum qubit and using entanglement. Okay, so if we see the for protocol of super dense coding kind of work like this way. So first Alice and Bob need to create an entanglement. Okay. And okay, so this is a bit of a funny picture, okay. So first Alice and Bob need to create entanglement. So as we said, they want to create this EPR pair beta 00. So one of them, so here we assume Bob is the one creating entanglement. So Bob will create a beta 00 by applying this Hedema and the CNAT gate. Okay, and so now this 2 qubit is in beta 00, and now we start our super dense coding. So we send one of the qubit to Alice and another qubit remain at Bob's side. Okay, so 1 qubit to Alice and another qubit to Bob. And Alice will do something on her register. So Alice said there are 2 bits Alice want to send. So there is the A1 bit and the A2 bit. And what Alice do is first apply X if A2 is 1, and then apply Z if A1 equal to 1. Okay, so Alice do this thing on her qubit and send back this thing to Bob. Okay, so this box is Alice, and now everything is on Bob's side. And we say Bob do Bell basis measurement, and now we can actually, because we know how to map from computational basis to Bell basis, then we reverse this circuit, we can map from Bell basis to computational basis. Okay, so to do Bell basis measurement, we just apply the inverse of this circuit and measure in computational basis. Okay, so we apply CNAT first and Hedema, and so this whole thing we apply CNAT, Hedema, and measurement. So this thing together is basically measuring in Bell basis. And yeah, so this is our super dense coding. Okay, and yeah, this is super dense coding in terms of quantum circuit. And also we can express our teleportation mode in quantum circuit too. So teleportation, we have actually 3 qubit. We have unknown qubit that is going to be teleported, and we have 2 qubit that was in entanglement. It was in beta 00. And I guess in this description we omit this creating entanglement part. So this is just starting beta 00. And we say Alice was holding the 2 qubit here, and Bob is holding the 3 qubit here. And so what Alice do is we were describing this in step by step. We're saying it was doing CNAT and doing Hedema and doing 2 measurement. But now we know this CNAT and Hedema is just translating from Bell basis to computational basis. So what Alice do is Alice just measuring in Bell basis. Okay. So what teleportation do is actually Alice measure her state in Bell basis and send the measurement result. So this N1 and N2 to Bob, and Bob will see what is N2, and if N2 is 1, we'll apply X, then if N1 is 1, apply a Z. Okay. And I guess we can kind of skip the calculation or DC teleportation calculation before. So we start with psi equal to arbitrary unknown state, and where we have a beta 00 here, and so we have step by step. So we go through here, and we go through CNAT, and go through Hedema, go through CNAT gate, and they will do something, and we go through Hedema gate. Excuse me. Yeah, and we go through Hedema, and finally we see the measurement result. Okay, and yeah, so this is teleportation in terms of quantum circuit, and then we can see what is happening in each step. So here we have after the measurement, there are 4 possible outcomes, and each one with 1 full probability, and at least will hold these 4 different computational basis states, and this will collect the Bob state into these 4 different states, 4 different unknown states, and Bob can do correction to make the state he hold actually into the original state. And I guess this is a bit nice time to. Okay, let's see if do this in 10 minutes. Okay, and finally is a bit of a tip. Okay, so this is not actually extra, but it's a very nice tip to do pen and pencil calculation. Okay, the paper and the pen calculation of those quantum circuits. Okay. And yeah, so we have been doing calculation in this way. When we want to calculate, so I guess a lot of homework problem and also midterm problem, I will ask you to calculate the output of a quantum state, output of a quantum circuit, or sometimes we will ask you to prove that the 2 circuits are equivalent. So maybe say this thing. Sometimes we want to prove this kind of thing. Okay. And the easy way to do this calculation is the way we have been doing. So we can just set the starting state with in computational basis. Okay, or we can just write the state of each time step in computational basis. Okay, and then when we can just apply the gate to the register using this what I call logical expression. Okay. So if we have some computational basis state, so with some unknown integer say a here, and then you can just write down all the gate we use most often as this logical expression. So you see the z to the a is just -1, z on a is just -1 to the a, and c naught ab, this we have seen a lot, equal to a and a plus b. And x on a is a plus 1. So this is just like in C naught, is 1 plus 1, just means you flip a. And cz on ab equal to this -1 to ab and b. Okay. And okay, so those 4 things are always nice because you see that you start with 1 computational basis state, you end up with another computational basis state. Okay. So this makes the calculation really nice. You don't increase the number of computational basis states. But then there is annoying thing that is Hedema. So Hedema 0 will become plus state, and Hedema 1 will be a minus state. Okay, and I guess I forgot to erase this thing. Okay. And so last year midterm was just until here, but this year we can teach a little more, so midterm can be do a little more. Okay, and anyway, so let's back to Hedema. Okay. So Hedema 0 give you the plus state, and Hedema 1 give you the minus state. And this will create a computational basis. So plus state actually is the plus state equal to 1 over square root 2. And 0 plus 1, and so wherever you have a Hedema, on the next step you need to trigger even more computational basis state, and this is what will happen if we actually do the analysis here carefully. So in a teleportation circuit, there is a Hedema here. So we start with, you see that we start with end state here. Yeah, we start with 4 state here. 1, 2, 3, 4. We start with 4 computational basis state, and after the Hedema, we end up with 8 computational basis state. And it's quite cumbersome, but after we do measurement, actually reduce the number quite a bit because well, I guess there are 4 outcomes, but each outcome there is much less state inside. Okay, so yeah, so this is a general procedure, and why do I like to describe this procedure is because well, it's compared to another procedure that you might think is more intuitive. That is, you just write down your state as a, so if you have n cubed, you can write down your state as a 2 to n dimensional vector, and every gate as a 2 to n by 2 to n dimensional matrix. Okay, and so technically you can do this. It's totally correct. It's done by linear algebra, but practically it's very hard to do this because there are just too many numbers to write. You need to write a lot of zero in your matrix, etc. So it's take a long time, and if you do this, it takes a long time, and it's very easy to make a mistake. So yeah, so you can do this, but I recommend you to do this thing. Okay? So you can just do calculation in this calculation on computational basis, and then you just run by superposition. So whenever you have entangled state, etc., then you can do superposition or linearity principle, and say just like and just do everything. So just like this here, you have this 0 component and 1 0 component, and then just do them separately, and then the result is just a linear combination of each result. Okay, and we have 5 more minutes. Let me take a peek of what's extra. We have a measurement in quantum circuit. I guess we can have this next time. Yeah, so it's about something I tried to say already. So we can say measurement is always in computational basis. And there is another thing that is you can actually defer measurement to the end, okay, by doing something like this. Okay, and so we will talk about this measurement principle a bit more next Tuesday, and we will have our midterm next Thursday. Yeah, I think it's on 8th week. Yeah, so see you on next Tuesday.